Hello, my name is Murat, and today I'd like to tell you about the work we have made with Konstantin Vorontsov. Its title is Learning Topic Models with Arbitrary Loss. Topic modeling is an area of statistical text analysis. For collection of documents with some vocabulary, we try to find a set of clusters called topics. Also, for each document, we want to find its distributions over topics. Each topic is a probability distribution over vocabulary terms. In most cases, topic models deal with bag-of-words text representation, where we only store and use information about terms counters, ignoring their positions in the documents. Formally, we have a vocabulary W, set of documents D, and bag-of-word matrix NDW. Our goal is to factorize NDW into two matrices called phi and theta. Topics are stored as phi columns, and documents distributions over topics are presented by the columns of theta. To find this factorization, we used log likelihood maximization with some constraints on resulting matrices values. Described model is called probabilistic latent semantic analysis, or PLSA. The local optimal point of the described problem can be found via EM algorithm. We initialize phi and theta with random values and then proceed iteratively a two-step process. On each step, we compute temporary variables PTDW, denoting the probability of topic T for term W in document D, and on M step, we use these variables to calculate new versions of parameters phi and theta. Additive regularization of topic models is an approach that allows to incorporate different user-defined constraints in the PLSA learning process. Such constraints should be presented as smooth functions and can be used in different combinations. To learn a regularized model, we can use the same EM algorithm with some changes in M step that are marked red on the slide. Here we can see two simple but efficient regularizers. The first one is a regularizer for phi matrix smoothing or sparsing. It is used in another popular topic model called latent directlet allocation. The second one is a topic decorrelation regularizer. We use it to increase topics diversity. At this slide you can see the main theoretical idea of our paper. We suggest that it is possible to replace the logarithm function in a log likelihood loss with any other smooth function L. In our paper, we formulate and prove a main theorem. It says that even with such modification, the problem still stays solvable. We only need to change the formula of each step in the way described on the slide. One of the possible applications is to use a linear function instead of logarithm. It leads to each-step version without need in normalization. As normalization usually requires a significant part of computation time, we call such each-step a fast one. Before we move to experimental section, I would like to note a bigger term topic modeling library we used in all our experimental studies. Its main advantage is an ability to build a regularized model using fast parallel learning algorithms. Also, it is worth noting that straightforward implementation of EM algorithm is very inefficient, and BigRTM has three most suitable options. They may avoid PTDW and theta storage and recalculate their values on the fly. Also, they move theta columns calculation on each step and can proceed several each step passes through one document before one M step for better convergence. Offline algorithm processes all documents before M step, so it requires several passes through collection. Online algorithms proceed M step once per given number of process batches of documents. so they are able to make only one pass through collection. A synchronous online algorithm has an additional feature. It performs M-step for previous generation of batches at the same time with processing E-step for new generation. Fast E-step avoids normalization procedure, but it is possible to speed up normal E-step significantly in case of sparse models. So we introduce some optimization for them. Pay attention that in case of model without storing theta matrix, we need to store phi matrix, NWT counters matrix, and optionally RWT matrix in case of regularization. All these matrices has the same size and are stored in the same data structure that we call phi-like matrix. Before the optimization, phi-like matrix was stored in a dense real-valued matrix. Storing all values for one term as one continuous array allows a local sequential access to elements during loops over topics. And E-step normalization is an example of such loop. It is efficient in case of dense models, but topic models are often very sparse, so a great amount of zero values wastes computation time. That's why we propose a hybrid format to store phi-like matrix rows. Dense rows are stored in a continuous arrays as before. To store sparse rows efficiently, we use 3 smaller arrays instead. First array contains all non-zero elements of the row. The second one contains original indices of non-zero elements. And the last one contains bitmap that marks whether the element of the row is 0 or not. These arrays allow us to reduce memory usage and skip 0 elements during loops over topics. We also can randomly access all elements with minimal costs. Okay, now we are ready to experiments. We test all 3 described algorithms on the subset of English Wikipedia and use 2 most common quality measures for topic models. Perplexity, which is a function of likelihood that shows the convergence of the model, and the average topic coherence that is known to be correlated with model interpretability for human. Firstly, we check whether our optimization really improves model training process in terms of elapsed time and peak memory usage. We studied models without regularization, with sparsification regularizer, and with both sparsification regularizer and our optimization. We also try a different number of topics and pass it through document per one collection pass. Brief results are shown on the slide. Generally, small models with one document pass are not affected by our optimization. In other cases, it allows offline algorithm to work faster, but without reducing memory costs on regularization. Online algorithm with optimization works faster and consumes the same amount of memory as base one. A synchronous algorithm usually consumes more memory than any other algorithm due to the need for storing several versions of matrices. So it receives the most from optimization and gets both reduction of training time and peak memory usage. At last, in the second set of the experiments, we studied the usage of fast and normal E-steps. At this slide, you can see training strategies. We've tried to achieve better results in terms of quality metrics that will be presented on the next slide. First 5 strategies are the different combinations of E-steps in PLSA model. The last 2 ones are the models with all normal E-steps and some regularization. We measured a training time and final values of model perplexity and coherency. For offline algorithm, we also measured these values on the finish timestamp of the fastest algorithm to check whether it is possible to get better results with some algorithm in a given time box. During the experiments, we tried different strategies, number of topics, and the frequency of M steps in number of process batches for online algorithms. For offline algorithm, we can conclude that topic decorrelation is a good choice for small models, but too slow for models with many topics. Using all fast E-steps gives significant training speed up, but in terms of perplexity, the resulting model is very bad. Half strategy, where first part of iterations is fast, and the second one is normal, seems to be a compromised solution, as it gives us better coherence without losing other metrics. For online algorithm, the situation with decorrelation is the same. Also, we can conclude that in case of the same updates frequency, all strategies with fast E-steps reduce training time, but spoil quality measures. Note that more frequent updates slow down any algorithm, but can improve the final model, so we decided to spend the time gain from fast E-steps usage on it. We've tried to use most perspective half model with more frequent updates, and it gave us very significant improvement of final perplexity compared to base model, with almost same values of train time and coherency. The results of asynchronous online algorithm study are similar to results of simple online one. Half strategy with more frequent updates loses some coherency, but gives more than twice gain in final perplexity value compared to base full model, staying significantly faster. It's also interesting that in some cases, full model with uniform sparsification gives results comparable to half strategy, with even lower training time due to storage and computation optimization. Here is a list of our main conclusions. We proposed and proved an ability to use different smooth loss function in topic model optimization functional. We experimentally find the best strategy of combining normal and fast E-steps by studying different strategies. We optimized work with sparse models in the BigR10 library and get some new results related to topic decorrelation regularizer. Thank you for your attention.